When an AI agent moves in a straight line, it strikes a barrier and shatters rather than routing around it. Modern LLM agents rarely solve non-trivial tasks in a single pass. They chain together search, retrieval, and API calls, but they suffer from greedy execution, picking the immediately obvious tool without accounting for missing prerequisites or downstream dead ends. Welcome back. I'm the bearded AI guy, and today we're analyzing the architectural gap between greedy and planned tool use, with help from our human architect. We are breaking down the ICLR 2026 paper ToolTree. It proposes a new planning controller that replaces one-shot tool selection with search over multi-step tool trajectories. In these complex tool chains, the value of the first move depends on what moves become possible later. Solving this foresight problem is currently the most significant hurdle in agent engineering. To understand why this search matters, look at the current standard. Frameworks like React rely on simple, interleaved think, then act reasoning traces. These linear traces are effective in closed-set environments, where the agent only has a handful of fixed, reliable APIs to choose from. But real-world deployment is often an open-set problem. This is a massive, noisy pool of endpoints, where retrieving the correct tool from the library is as difficult as using it. Take the tool bench benchmark, for example. It requires agents to navigate over 16,000 different API endpoints. In a 16,000 tool environment, a greedy choice at step 1 almost guarantees a fatal prerequisite error by step 4. Local decisions become unreliable when inter-tool dependencies are high. This scaling problem shows that simple prompting has limits. We have to move from linear text generation to algorithmic look-ahead search. To create that look-ahead, the ToolTree authors adapted Monte Carlo Tree Search, or MCTS. This is the same decision-making algorithm used to solve the massive branching spaces and game-playing systems like AlphaGo. ToolTree maps the tool sequence into this MCTS structure. The nodes in this tree represent the evolving dialog state, which includes the current context window and the intermediate results of previous tool executions. The edges connecting those nodes represent the tool invocations, the specific API call, and the arguments the agent has drafted for it. The algorithm runs multiple simulated rollouts down these branches, looking ahead to see which trajectories lead to a successful task completion. By mapping tool planning to a tree, the value of the first API call becomes a direct function of every subsequent tool invocation in that specific branch. Exploring a tree is only useful if the system can accurately score the branches. Without a way to measure progress, the agent is just guessing. ToolTree introduces a dual feedback loop. First is the pre-execution assessment, or Foresight. An LLM judge scores the tool call based on metadata and context before it runs. This pre-eval score biases selection and determines if a node can expand further down the tree. But Foresight is still just a prediction. To be accurate, the system needs to know what actually happened when the API was called. This is the Hindsight mechanism. After execution, a judge scores the grounded utility of the data returned by the tool. This utility score is back-propagated up the tree. Earlier decisions receive credit or blame based on real-world outcomes rather than hypothetical thoughts. This loop forces the agent to align its internal plans with the hard reality of execution. The cost here is the obvious concern. Running dozens of rollouts with multiple LLM judge calls for every step would rapidly deplete an API budget. To manage this, ToolTree uses bidirectional pruning, which dynamically severs unproductive branches to save compute. Pre-pruning discards candidates before execution if they look low yield, using a threshold and top K gating. Post-pruning marks branches non-expandable if execution feedback proves they are unproductive or result in typed error tokens. The paper includes an ablation study on the GTA benchmark to show which parts of this architecture are actually doing the heavy lifting. Removing the post-evaluation signal causes a much larger drop in accuracy than removing pre-evaluation. This confirms that retroactive credit assignment, judging after the fact, is the necessary fix for myopic tool selection. We've seen the accuracy gains, but we also have to look at the deployment realities of test-time search. ToolTree reports an average improvement of about 10% over prior planning paradigms across 4 benchmarks. But to get that 10%, a single final action now requires dozens of hidden LLM judge calls and internal tool probes. This chart plots runtime against the step budget. Runtime grows linearly, climbing into the hundreds of seconds and approaching 1,000 at the highest limits. It is significantly slower than greedy agents like React, trading absolute speed for precision. This is the latency paradox. Multi-hop accuracy is improving, but the compute cost is currently too high for real-time user experiences. If it takes minutes to finalize a plan, where does this framework actually belong? This architecture is currently incompatible with sub-second chat interfaces. Its real home is in asynchronous, high-stakes background jobs, like financial reconciliation or autonomous research, where a wrong toolchain is expensive and extra minutes of search are acceptable. We are seeing the center of gravity in AI engineering shift from training time learning to inference-time search. If you want to keep up with these shifts, subscribe to the channel. Let me know in the comments how you're handling toolchain latency and API costs in your own agent builds. If an agent is executing a complex API chain, you have to spend the compute to let it look ahead. I'll see you in the next one.